So in the last lecture, we established what the sinoatrial node, the SA node, is. Okay, it is located in the upper right atrium of the heart. It is a collection of cardiac muscle fibers that looks just like all the other cardiac muscle fibers in the heart, except the SA node is a special collection of cardiac muscle fibers that are capable of generating their own action potentials. This is the image that we looked at rather closely in the last lecture, and I said you have to imagine the purple dot, which is supposed to be a depiction of the SA node. You have to imagine this purple dot as just a collection of cardiac fibers that look just like the other cardiac fibers that make up the right atrium. The difference being, of course, that these cardiac fibers right here in the sinoatrial node, or that make up the sinoatrial node, are capable of generating their own action potentials. And then we went through the whole process by which these sinoatrial node muscle fibers, cardiac muscle fibers, are capable of generating their own action potentials. We went through the funny channels and how that gets them to threshold, and then they propagate an action potential utilizing calcium. And then we went through the repolarization process, and we said that the SA node, these cardiac muscle fibers that make up the SA node generate about 70 action potentials per minute on average. Okay, and what do we know about the heart rate? Heart rate is about 70 beats or 70 contractions per minute. That means your heart contracts as a whole about 70 times per minute. So that is clearly related to what these sinoatrial node cardiac muscle fibers are doing, right? They're generating 70 action potentials per minute, and somehow the generation of these action potentials is causing the entire heart to contract. And that's what we need to focus on now, is we need to try to figure out how, when these sinoatrial node cardiac fibers generate action potentials, does that cause the entire heart to contract? What you're looking at here is another silly depiction of the sinoatrial node. Now it's red for some reason. Who knows why they decided to do that this time? Sometimes it's purple, sometimes it's red, sometimes it's yellow. It never ceases to amaze me, all of the different ways, incorrect ways, they depict the SA node. So this is the SA node. What is the SA node actually? Well, it's cardiac muscle fibers. The SA node should look just like these cardiac muscle fibers that lie next to it. So let's be clear about what's being depicted here. Okay, what it's showing is the SA node, which is a collection of cardiac fibers. And where is the SA node located? The SA node is located in the upper right atrium of the heart. And what's lying next to the SA node are what we would call the true contractile fibers of the right atrium. Okay, all of these are what are called, again, contractile fibers of the right atrium. Okay, but I need to be clear. I know I've said it a million times, but it's really important. These SA node fibers, to the naked eye, would be really indistinguishable from these cardiac fibers. Okay, so these are SA node fibers, which are part of the right atrium, by the way, and these are true contractile fibers. And the point I'm trying to make here and show you is that the SA node fibers are actually physically attached to the contractile fibers of the right atrium. Right? The SA node fibers and the contractile fibers are all part of the right atrium, right? But they have different functions, as you're about to see. Okay, the big point here is the SA node fibers are physically attached to the contractile fibers of the right atrium. Okay, now, how are they attached to one another? They're attached to each other through what are called intercalated discs. Okay, so if you look over here on the right, what you're seeing is one cardiac muscle fiber. And you're seeing that that cardiac muscle fiber is actually attached to another cardiac muscle fiber. And the way that they're attached to each other is through what's called an intercalated or intercalated disc. Okay. That's what attaches cardiac muscle fibers to each other. I said this in the last lecture. Cardiac muscle fibers are not mutually exclusive. They're actually all physically attached to each other. And they're attached to each other through these intercalated discs. You see this, all these little squiggly lines? Those are all what are called intercalated discs. And what they're doing is they're attaching the different cardiac muscle fibers to each other. That doesn't happen in skeletal muscle. Okay, skeletal muscle fibers aren't attached to each other, but cardiac muscle fibers are attached to each other. So what makes up an intercalated disc? Two things. First of all, there's basically what would be referred to as kind of the staple, and that's right here. This is what's called a desmosome. A desmosome is just kind of let's imagine a staple. It holds the two cardiac muscle fibers together, and it maintains their integrity during contractions. It's very important, the desmosome, but it's actually not the part of the intercalated disc that we're really interested in. The part that we're interested in is what's called the gap junction. The gap junction is the second part of the intercalated disc. And by the way, there's hundreds and thousands of desmosomes, and there's hundreds and thousands of gap junctions that make up one intercalated disc. Okay, so don't get the idea that an intercalated disc is only made up of one desmosome and one gap junction. It's a simplification, just like everything that's done in textbooks. Anyways, the gap junction. The gap junction is a tunnel that exists between the two cardiac muscle fibers. It's actually a tunnel that ions in particular can travel through. Imagine as like an ion pore, actually. It allows positively charged ions to kind of flow and move between the two fibers. So that's the two things that make up an intercalated disc. Intercalated discs are made up of desmosomes, and there would be many desmosomes if this was a real image. Okay, intercalated discs are made up of desmosomes, and intercalated discs are also made up of gap junctions. Those are the two things that make up intercalated discs. Okay, and intercalated discs, what do? The intercalated discs are how cardiac muscle fibers are attached to each other. It's just that within the intercalated disc, there are the desmosomes, which serve as the staples, and the gap junctions, which serve as the tunnels. So the point of going through all of that anatomy was to say that the SA node fibers, right, the SA node cardiac fibers are attached to the true contractile fibers of the right atrium through intercalated discs. So here's what I want you to do. I want you to look at this image over here on the right, and I want you to pretend that this is an SA node cardiac fiber. It's this one right here, okay, that I just drew. This is an SA node fiber, and attached to it through an intercalated disc is a true contractile fiber. It's actually this contractile fiber right here. Okay, so that's what you have to pretend that you're looking at. I know that's not what the image says it's showing, but that's what I want you to pretend that you're seeing. I want you to pretend that you're seeing an intercalated disc that exists between an SA node cardiac fiber and a contractile fiber of the right atrium. You can see that the SA node fiber is attached to the contractile fiber of the right atrium. They're both part of the right atrium. One's just an SA node fiber and one's a contractile fiber, but they're attached to each other through this intercalated disc, which is made up of desmosomes and gap junctions. And then you say, well, what's the relevance of discussing this as it relates to how in SA node fiber generating an action potential causes the whole heart to contract? So let's try to explain that. Okay. Here is the SA node fiber again. And what I want you to do is pretend that the SA node fiber has generated an action potential. You know that the SA node cardiac fiber does that on its own. but it generated an action potential, and the action potential is propagating down the SA node fiber. How does it do that? How does it propagate down the fiber, right? With calcium. These L-type voltage-gated calcium channels keep opening up, and calcium shoots in. Drives the interior up to positive 10 or something, moves to the next region where it's still negative, makes that region positive, right? The wave of positivity, the calcium ions move to the next subsequently negative region, make that region positive, and now by making that region more positive, depolarizing it, these more L-type voltage-gated calcium channels open, calcium shoots in, drives this region up to positive 10. Okay, so the point is, the action potential is propagating down the SA node fiber. Now, what's the SA node fiber attached to? The SA node fiber, through an intercalated disc, is attached to a true contractile fiber of the right atrium. Okay, what does this mean? Well, the contractile fiber, actually, this is where things can get a little confusing, but it'll make sense as we progress. The contractile fibers, the true contractile fibers, they actually have resting membrane potentials. They're not autorhythmic, right? They're not autorhythmic cells. They can't generate their own action potentials. They actually have resting membrane potentials, just like skeletal muscle fibers do. All of these over here, these true contractile cardiac muscle fibers, they all have resting membrane potentials. And the resting membrane potential is right around negative 90 millivolts, much like a skeletal muscle fiber. Okay? So, kind of amazing, right? The SA node fibers, compared to the contractile fibers, which they're actually attached to through intercalated discs, are very actually different from each other as it relates to kind of, neurophysiology. Not neurophysiology, I mean electrophysiology, excuse me. By that I mean they're different from each other in terms of electrophysiology in that the SA node fibers don't have resting membrane potentials, constantly fluctuating, generating their own action potentials, and the contractile fibers, which they're directly attached to through intercalated discs, do have resting membrane potentials. And they don't generate their own action potentials. Okay, so what does all of this mean? All right, if the contractile fiber that is directly attached to the SA node fiber, as is being depicted in my image here, if the contractile fiber has a resting membrane potential of negative 90, and the interior of the SA node fiber right now, at least underneath the plasma membrane in this specific region, is positive 10, okay, and that's due to an influx of calcium ions into the SA node fiber, what do you think is going to happen? Okay, it should be fairly clear here. Okay, you've got an influx of calcium ions inside of the SA node fiber, making the inside of the SA node fiber positive in that region. Well, adjacently, in the contractile fiber, it's negative 90. And look at this. What's part of the intercalated disc that enables the SA node fiber to be attached to the contractile fiber? One of the things that makes up the intercalated disc is a gap junction. And the gap junction is a literal ion tunnel that calcium ions, because they're positive, can travel through. So you look at this and you say, well, what's going to happen? Well, this wave of positivity, these calcium ions that are now within the SA node fiber, are just going to get pulled over into this subsequent area of negativity, which is inside of the contractile fiber, where it's negative 90 millivolts. That's the point of the gap junction. It enables, in this case, you're going to see it's going to be different with other fibers, but in this case, it allows these calcium ions, this wave of positivity, to move over into the contractile fiber. Right? Because in the contractile fiber, it's negative 90 millivolts. So of course, this wave of positivity, these calcium ions, are just going to rip right through the gap junction, this tunnel, over into the subsequently negative region, which is inside of the other cardiac muscle fiber, the contractile fiber. And then you say, well, what's going to happen as this wave of positivity, these calcium ions, travel through the gap junction from the SA node fiber into the contractile fiber. Well, of course, if calcium ions are flowing into the contractile fiber, calcium ions are a positive ion, and if they're flowing into the contractile fiber, they're going to depolarize the contractile fiber. It's going to make the contractile fiber more positive because the contractile fiber is going to start gaining positively charged calcium ions from the SA node fiber. So what I'm saying here is these calcium ions that are coming from the SA node fiber into the contractile fiber are going to begin to depolarize the contractile fiber. It's going to make the contractile fiber more positive. I've said this a million times in the class, but I'm just, as I was going through this, was thinking to myself, have you ever really explained this? Because I think I've just kind of taken for granted and assumed that it's logical and that you understood it, okay? Which is always a mistake for somebody to do. So I'm just going to say this real fast. Why do areas of positivity want to head towards areas of negativity? Right? The answer seems obvious, but let's just be clear. Okay? What's creating the wave of positivity inside of the SA node fiber anyways? Well, calcium ions. Calcium ions flowing into the SA node fiber are what is making the interior positive, right? In that specific region, at least. The influx of these positively charged calcium ions is what's making the inside of the SA node fiber in this region depolarize and become positive 10. Right? The reason that region is positive 10 is because of an influx of calcium ions. They are what make up this wave of positivity. Okay, great. What about in the contractile fiber? In the contractile fiber, it's negative 90. Okay, very negative. Right? It has a resting membrane potential of negative 90. So why does this wave of positivity in the SA node fiber, which is created by calcium ions, want to move into a subsequently negative area inside of the contractile fiber? And the answer is because there's a really, really potent negative electrical driving force in the contractile fiber. Inside of the contractile fiber, it's negative 90, right? That's its resting membrane potential. That's a very strong negative electrical driving force. What's creating this wave of positivity, positive 10, inside of the SA node fiber? What's creating that wave of positivity are positively charged calcium ions. Well, where are positively charged calcium ions that are creating this wave of positivity going to get pulled towards? Well, they're going to get pulled towards negative areas due to a negative electrical driving force. Right? There's a very strong negative electrical driving force in the contractile fiber of negative 90. That means the contractile fiber is going to pull positively charged ions towards it. What's over in the SA node fiber right now? A whole bunch of positively charged calcium ions creating a wave of positivity. So these calcium ions that are creating this wave of positivity, since they're positive, are going to get pulled towards areas that are negative due to the strong negative electrical driving force pulling them in that direction. There's also a diffusion gradient, right? It's high. The calcium concentration is higher right now over in the SA node fiber than it is over in the contractile fiber. That's really a moot point to make, because the major thing that's pulling the calcium ions, the wave of positivity, over into the contractile fiber is the fact that the contractile fiber has a very negative electrical driving force and the calcium ions are positive, so they're going to get pulled towards areas where it's very, very negative, right? Because of this negative electrical driving force that pulls positively charged ions towards it. So this is the explanation why areas of positivity, quote unquote, move towards areas of negativity, right? It's fairly, I think in my head, obvious, but maybe when you lay it out, it isn't as obvious as I assume it is. So I hope that was helpful. Maybe it was a waste of time. In that case, I apologize. Back to the real discussion. Here is the SA node fiber. Here is the contractile fiber. And the SA node fiber is attached to the contractile fiber through intercalated discs. What are intercalated discs made up of? Desmosomes and gap junctions. Okay, what was the SA node fiber doing? Propagating an action potential, utilizing calcium, right? So calcium was shooting in, making the interior positive, positive 10. And then where did the calcium ions go? The wave of positivity, right? It traveled through the gap junction from the SA node fiber into the contractile fiber, where it was negative 90. The reason that the wave of positivity, the calcium ions, got pulled from the SA node fiber into the contractile fiber is obviously due to this strong negative electrical driving force. Okay. Now, as the calcium ions, the wave of positivity, moves from the SA node fiber into the contractile fiber is going to be gaining all these positively charged calcium ions, and that's going to cause the contractile fiber to depolarize, right? Become more positive. And as the contractile fiber depolarizes, you think, well, what could possibly happen? You've seen this a million times throughout the class. The contractile fiber can be depolarized to threshold. As more calcium comes into the contractile fiber, it will depolarize the contractile fiber to a greater and greater degree. And let's say that it goes up about, it becomes 15 millivolts more positive. So from negative 90 to negative 75 millivolts. If we can get from negative 90 to negative 75 millivolts, then the contractile fiber will hit threshold. And when it hits threshold, it would be in a specific region, let's say right here. If the contractile fiber hits threshold, then what opens are voltage-gated sodium channels. I said that right. Sodium channels. I didn't say calcium channels. When the contractile fiber gets to threshold, what opens are voltage-gated sodium channels. In the SA node fiber, when you get to threshold, voltage-gated calcium channels open up. Yet again, we're seeing big differences between SA node fibers, we're seeing big differences between SA node cardiac fibers and contractile cardiac fibers. Okay? When you get the contractile fibers to threshold, voltage-gated sodium channels open up. And what do we know about sodium? Sodium's high outside of the cell. It's low inside of the cell, so it has a chemical driving force to come in. The interior is negative 90, so there's a potent negative electrical driving force pulling it in as well. So if you open up a whole bunch of sodium channels, you can imagine what's going to happen. Sodium is going to shoot in to the contractile fiber, right? And you would say, now the contractile fiber is going to generate an action potential, which is true, but unfortunately, there's a lot more to be said about this compared to other types of muscle fibers that we've discussed, or neurons, okay? So it is true, if you get the contractile fiber to threshold, then the voltage-gated sodium channels will open up, sodium will shoot in, let's say depolarize the interior to positive 10 or positive 20 or something like that. But there's something else very important that happens along the way, okay? And that's what we need to discuss here. So this time, we'll focus in much more heavily on the contractile fiber and less on the SA node fiber, okay? The SA node fiber allowed calcium to travel into the contractile fiber through the gap junction, which depolarized the contractile fiber to threshold. Then, voltage-gated sodium channels within the contractile fiber opened up. When we got from negative 90 to negative 75, right, we got to threshold. Now these voltage-gated sodium channels opened up. Sodium begins to rush in. Okay. Now, when the interior gets to about negative 50 millivolts, and that's due to the sodium ions flowing in and depolarizing the contractile fiber in this region. As it moves from negative 75 up to negative 50, there's something else very important that happens. At negative 50, there are also voltage-gated calcium channels, the L-type calcium channels. This is going to become very important. Okay? There are also these voltage-gated calcium L-type channels that exist throughout the membrane of the contractile fiber as well. And at negative 50 millivolts, they open up, just like in the SA node fiber. So at negative 50 millivolts, the voltage-gated calcium channels, the L-type channels, open as well. And what happens is calcium shoots in, right? Because calcium's high outside, it's low inside, has a chemical driving force to come in. It also has a strong negative electrical driving force to come in, right? We could just say electrical driving force to come in. So if you open up calcium channels, calcium will shoot in. And it's actually then both sodium and calcium that drive the interior of the contractile fiber up to +10 or +20. It's not just sodium. Let's be real clear on this because this fact is very important for cardiac muscle. Okay, here's the contractile fiber. Here's the SA node fiber, as calcium comes from the SA node fiber over into the contractile fiber, through the gap junction, it depolarizes the contractile fiber to threshold, -75. That causes these voltage-gated sodium channels to open up. Then sodium rushes in. Okay? The influx of sodium into the contractile fiber will depolarize it to -50 and beyond, but first -50. And at -50, that causes the voltage-gated calcium channels, the L-type channels, to open. And then calcium shoots in, as well as sodium. It's not that the sodium channels shut at -50. At -50, what you'll have is you'll have both sodium and calcium channels open. Both sodium and calcium will be flowing into this contractile fiber, and collectively, both of them depolarizing it to like +10 or +20. Okay, now over in the adjacent portion of the contractile fiber, it's still -90. So where's this wave of positivity going to go? And the wave of positivity is not just sodium ions, it's sodium and calcium ions. So where's this wave of positivity going to go? It's going to go into the adjacent region of the contractile fiber. And now, in this adjacent region, what do you think happens? The adjacent region is going to get depolarized from -90 to -75, and then what's going to open up? Well, first, the voltage-gated sodium channels will open up. At -75, sodium will shoot in. And then the influx of sodium will depolarize the contractile fiber from -75 to -50. And then what happens? The voltage-gated calcium L-type channels will open up, and calcium will flow in. And the influx of calcium and sodium together will depolarize the interior up to whatever, +10. And then what's going to happen? This wave of positivity is going to head towards a subsequent area of negativity, right? And what's going to happen over in this region? First, voltage-gated sodium channels will open up, depolarizing this region to -50. Then, voltage-gated calcium channels will open up, and the influx of both sodium and calcium will depolarize this region to +10. What is the overarching point here? Contractile fibers contractile fibers propagate their action potentials utilizing both sodium and calcium together. Okay? Very important point. I will explain later on why this is so important, but it is fundamentally important to understanding the contraction of cardiac muscle fibers. Okay? If this is a contractile fiber, this contractile fiber is going to propagate its action potential utilizing both sodium and calcium. I'm drawing the calcium channels in blue. Okay. The influx of both sodium and calcium will drive the interior up to +10. Then it'll move to the next region where it's -90. Depolarize at 15 millivolts. Then the voltage-gated sodium channels will open up. Sodium will rush in, drive the interior to -50. And at -50, the voltage-gated calcium channels will open up. And then the influx of calcium and sodium at -50 will drive the interior up to +10, and then it'll move to the next region, and the exact same thing, the exact same process will repeat. First, the voltage-gated sodium channels will open up. Sodium will rush in, drive the interior to -50 from -75. Then the voltage-gated calcium channels will open up. Calcium will shoot in with sodium, drive the interior to +10. Look at contractile fibers propagate their action potentials utilizing both sodium and calcium. This point is going to make absolutely no sense until the next coming lectures, okay? But that doesn't mean that you don't have to understand it right now, because I won't emphasize it as much when we get to what would be referred to as excitation-contraction coupling of cardiac muscle fibers. You have to realize this. It's very important. So many drugs, cardiovascular drugs, and heart disease and heart problems are the #1 problem that people face clinically, excuse me. So many drugs revolve around our understanding of the fact that sodium and calcium are used to propagate action potentials by contractile cardiac muscle fibers. We use countless drugs to target these channels and to influence arrhythmias and different diseases of the heart. Okay, so you'll see why all this is so important, but you got to understand it for now. By that, I mean you've got to understand this without any context for the moment, which is always challenging, but it'll all come together. Anyways, this is an image that you've seen before. Okay, here's the SA node, which really, this should be a depiction of more cardiac muscle fibers. All right. What do the SA node fibers do? They generate their own action potentials. And what happens? When the SA node fibers generate their own action potentials, the action potentials propagate down the SA node fibers. And then what happens? The action potentials that the SA node fibers generate and propagate they actually move into, another way of saying this is they're passed to the contractile fibers that they're attached to. Right? The action potential, which is again a wave of positivity due to the influx of calcium ions into the SA node fiber, the action potential propagating down the SA node fiber will actually move into the contractile fiber. Again, what is an action potential? An action potential is a wave of positivity that travels down a cell. Okay, a non-decremental wave of positivity electricity that travels down a cell. So the SA node fiber generates an action potential, right? This wave of positivity that travels down the SA node fiber. And thanks to the intercalated discs, more specifically the gap junctions that make up the intercalated disc, that action potential, that wave of positivity can actually move into or be passed to the contractile fiber that the SA node fiber is attached to. If the SA node fiber generates an action potential, then the contractile fiber will generate an action potential, because the action potential, that wave of positivity, will actually move from the SA node fiber into the contractile fiber and cause the contractile fiber to generate an action potential. So this isn't just like a full stop. Right? It's not that we just want SA node fibers to generate action potentials and that's it. The purpose of SA node fibers, these autorhythmic cells, these autorhythmic cardiac muscle fibers, the purpose of these SA node cardiac muscle fibers generating their own action potentials is to actually pass those action potentials to the cardiac muscle fibers that they're attached to. By that I mean the purpose of SA node fibers generating action potentials is so that the cardiac fibers that lie next to them that they're attached to, it's so that those cardiac muscle fibers will also generate action potentials. That's the point of the SA node fibers generating action potentials. And then that brings us to a greater point here, which is, what about these contractile fibers, which are all now generating action potentials, right? These SA node fibers generated action potentials, and they passed those action potentials to the contractile cardiac fibers that they're attached to. through these intercalated discs. And now these contractile fibers are generating action potentials, propagating action potentials. What's going to happen? Well, this contractile fiber here, if you see, it's attached to another contractile fiber. And this contractile fiber is attached through intercalated discs to another contractile fiber. Look at this, right? Here's one contractile fiber. Here's a second contractile fiber. 1, 2. Here's another contractile fiber. 3. Here's another contractile fiber. 4. Look at that. Contractile fiber number 1 is attached to contractile fiber number 2 through an intercalated disc. Contractile fiber number 2 is attached to contractile fiber number 3 through an intercalated disc. Contractile fiber number 3 is attached to contractile fiber number 4 through an intercalated disc. So you get to this and you say, well, what's going to happen then? Well, it should be fairly obvious. Here is the SA node fiber. Here is contractile fiber number 1. Here is contractile fiber number 2. Here is contractile fiber number 3. Contractile fiber number 1 is attached to contractile fiber number 2 through intercalated discs and thus gap junctions. Contractile fiber number 2 is attached to contractile fiber number 3 through intercalated discs and thus gap junctions. So what's going to happen? Well, as the action potential propagates down contractile fiber number 1, and that is through both sodium and calcium, by the way, not fundamental to this conversation, but nonetheless, remember, the contractile fibers propagate their action potentials utilizing both sodium and calcium, okay? That's what's causing this wave of positivity, this action potential, to travel down contractile fiber number 1. And then what's going to happen? The action potential, this wave of positivity, is going to travel into or be passed to contractile fiber number 2. And that's going to cause contractile fiber number 2 to generate an action potential, right? The influx of calcium and sodium ions into contractile fiber number 2, the action potential moving into contractile fiber number 2 is going to cause contractile fiber number 2 to get to threshold, depolarize, and generate an action potential. And then contractile fiber number 2 is going to generate an action potential. The action potential is going to propagate down contractile fiber number 2. What is the action potential? It's this wave of positivity due to calcium and sodium ions. That's what's causing the wave of positivity. And okay, well, what's going to happen? The action potential, this wave of positivity, is going to move into or be passed to contractile fiber number 3, right? That wave of positivity, these calcium and sodium ions are going to move into contractile fiber number 3, and it's going to depolarize contractile fiber number 3 to threshold, and contractile fiber number 3 is going to generate and propagate an action potential. A non-decremental wave of positivity due to both sodium and calcium ions. And then that action potential, that wave of positivity, is going to move into or be passed to contractile fiber number 4 that number 3 is attached to due to the fact that the calcium and the sodium ions, the wave of positivity, will move through the gap junctions into contractile fiber number 4 and cause contractile fiber number 4 to hit threshold. It is a domino effect of action potentials, which now hopefully starts to enable us to see the big picture. So the big overarching point of all of this is that all cardiac muscle fibers in the heart are attached to other cardiac muscle fibers through intercalated discs. That is huge, right? All cardiac muscle fibers in the heart are attached to other cardiac muscle fibers through intercalated discs. And what do those intercalated discs do? They allow one cardiac muscle fiber to pass an action potential to another cardiac muscle fiber. So when one cardiac muscle fiber generates an action potential, that action potential will move into another cardiac muscle fiber, and that cardiac muscle fiber will generate an action potential. And when that cardiac muscle fiber generates an action potential, the action potential will move into the next cardiac muscle fiber that cardiac muscle fiber is attached to, and the next one in line will generate an action potential. So collectively, you can say, well, what's going to happen here? Well, the SA node, these special cardiac muscle fibers in the upper right atrium that can generate their own action potentials, right? The SA node fibers, these pacemaker cells or autorhythmic cells as they're called, right? They can generate their own action potentials. Okay? And the SA node fibers, they generate their own action potentials. You've seen how they generate their own action potentials. And when they generate an action potential, what do? The action potential moves into the cardiac muscle fibers that they're attached to through intercalated discs, and then those cardiac muscle fibers, called contractile fibers of the right atrium, start generating action potentials. And then when those contractile fibers generate an action potential, what happens? The action potential moves from those contractile fibers into the next contractile fibers that those contractile fibers are attached to, and then those next contractile fibers generate an action potential. And then the action potential progressively propagates through all of the contractile cardiac muscle fibers of the heart. And we haven't gotten to this yet, but what do you think an action potential does to a cardiac muscle fiber, specifically the contractile ones more importantly? It causes them to contract. That's what action potentials do to muscle fibers. Action potentials cause muscle fibers to contract, whether it's a skeletal muscle fiber or cardiac muscle fiber. We haven't discussed it yet, but that action potential is going to cause those contractile fibers to contract. So the point is, if the SA node, these SA node cardiac muscle fibers, generate action potentials on their own, those action potentials that the SA node fiber generates will ultimately move throughout and be passed to all the contractile cardiac muscle fibers of the entire heart, right? Because they're all attached to each other through intercalated discs. So through a domino effect, this action potential that starts in the SA node fibers will rip throughout all of the contractile cardiac fibers of the entire heart. And it will actually cause the entire heart to contract. We call that a heartbeat. That's how your heart works. Okay? In the upper right atrium of your heart, there's a specialized group of cardiac muscle fibers that we call the sinoatrial node. And that special group of cardiac muscle fibers is special because they generate their own action potentials. And then because of intercalated discs, those action potentials that they generate get passed to all the cardiac muscle fibers in your entire heart. And all of the cardiac muscle fibers in your entire heart ultimately generate action potentials, and they all contract, and it ultimately happens simultaneously because the action potentials rip through these fibers so fast. That's a conversation for the next lecture, okay? I just want you to see the pathway here. There are plenty of intricacies, like why does the left and right atrium contract before the left and right ventricles contract? There's much more to this. But you've got to understand this big overarching point first. Okay? Every single time that the sinoatrial node fibers generate an action potential, that action potential is going to propagate through the whole heart, all the cardiac muscle fibers, contractile fibers of the heart, and the whole heart is going to contract. So the point is, if the sinoatrial node, these fibers, generate 70 action potentials per minute, okay, what's going to happen? If the sinoatrial node fibers generate 70 action potentials per minute, that means that 70 action potentials per minute are going to propagate throughout all of the cardiac muscle fibers, contractile fibers of the entire heart, and the entire heart is going to contract 70 times per minute. We call that a heart rate of 70 beats per minute. This is where the term pacemaker cell comes from, because it sets the pace by which the heart contracts. If the heart contracts 70 times per minute, that's because of the fact that the sinoatrial node fibers are generating 70 action potentials per minute, because every time that the sinoatrial node fibers generate an action potential, that action potential propagates throughout the entire heart, and the entire heart contracts. So if they generate 70 action potentials per minute, then the entire heart is going to contract 70 times per minute. The sinoatrial node fibers are autorhythmic. They generate their own action potentials, and they set the pace, the heartbeat, the heart rate of your heart, right? So they're autorhythmic pacemaker cells, Okay, that's where all these different terms come from. In the next lecture, we'll address how the action potentials actually cause the cardiac muscle fibers to contract, so excitation, contraction, coupling. And we'll also talk about some of the things that I briefly mentioned, which was the action potentials actually propagate through the fibers so fast that they all pretty much contract in unison. And what helps with that too are these things called conduction fibers, which we'll talk about. You've probably learned about the conduction system, but there's an intricate physiology to the conduction system that we need to discuss. And that will also help us understand, for example, why the left and right atrium contract before the left and right ventricles contract. So we'll get into all of that in the coming lectures. There's much more to discuss.